the video segment for chapter 5 of my textbook. The title of the chapter is Buckling of a Cylindrical Composite Panel with a Hole. Okay, so let me show you the drawing here. We have a cylindrical panel, okay, with a central hole in it, and the four sides of this are all simply supported, okay? And this is being compressed. This is being compressed by an in-plane load. Okay. So of course, in order to do this, if this drawing doesn't make sense unless you either apply the same force N on the other side, or assume that this edge here at the far edge is actually preventing to move in the Z direction, and it's being compressed from one side. Okay, we'll worry about that thing later on. The dimensions are given here, and actually this work dates back to a PhD thesis that was written back in 1985 and at Stanford University, and the reference is given in the book. And you can see why something like that is important. For example, if you look at this aircraft fuselage, the panel here is more or less is the drawing that I have on the side, okay, except that things are simplified. This window cutout is represented by a circle, etc. But this was the motivation behind it back then. And this thing that I was talking about a second ago about fixing displacement in Z and then looking at this thing from one side is also represented in this drawing. Okay, so simply supported means that ux and uy with respect to this coordinate system, which is going to be incidentally my rosette, uh, uh, there's zero, and then to prevent rigid body motion, we also assume that displacement in the z direction is zero. So the composite panel is made of 16 layers symmetrically laid out like that, and the material properties are all given here. There's a mistake there. This should be 0.28, not 0.25. Let me see if I can fix this. Oh yeah, this should be 0.28. Please, I'm sorry, not 0.28, 0.38. This is a mistake, 0.38. Okay, and uh, the experimental results and some finite element results were conducted back then, and the buckling load, critical buckling load, was arrived at this number, 24,000, roughly 24,000 pounds. Okay, so we'll worry about this thing later on. All right, let's go ahead and do this thing. Okay, an arc centered here. Put some angle, it really doesn't matter. We're going to fix that. Okay, then I'm going to draw what do I make the dimension of this thing 15 inches first? All right, this thing. Now I'm going to draw two construction lines, one from this end to that end, and another one from this end to this end. Okay. Well, first we make this thing symmetric with respect to that vertical axis. So this endpoint control that endpoint, control the middle axis. We're going to make it symmetric. Okay, and then we put an angle of 55.6 between these two. So between this line and that line, 55.6. Okay, and these two lines, I don't need it anymore. I can either I can take it into construction or I can just delete it. So let me go ahead and just delete it. Okay, its sole purpose was to create this geometry that you see here, and then we're going to exit. Okay, we will now extrude this curve in the vertical direction. Okay, so in order to extrude, you go to surface and extrude this arc, and we click on that guy, which will do it symmetrically, up and down, 7 inches in each direction, a total height of 14 inches. Okay. All right. So that's what we got. Now, we have to make a hole here. There are different ways of doing this problem or any problem. So this is the way I'm going to approach it, and it's consistent with what's done in the book. So on this plane, namely on the that'll be the YZ plane, I will sketch, and I'll sketch a circle of radius 1, centered at the origin, radius 1 or diameter 2, exit, and we'll extrude a cylinder from here, uh, longer right there. Okay. Now in the book I didn't do it mirror extend, so oh yeah, that's what it is. And we say okay. Now this is going to be used to split that surface. In order to split, you go to the transform. There is a surface split. You can see that. And read that carefully. It says element to cut. Element to cut is that cylindrical panel, and the cutting element is this cylinder that we created. And we say okay. There we are. Now we don't need this. We don't need this cylinder, except that because you use it to create that split, you cannot delete it. But you can always hide it. There we are. Okay. Anything that you don't want, you can hide. Like this sketch I don't want, I'm going to hide. Okay, very good. And this other sketch too, sketch 3 actually, I don't want, I'm going to hide it also. All right. So first save. Okay, the last thing that I want to do is to extract the boundary of this panel, because later on I'm going to use the zone method, and in order to use the zone method, you use the boundary of the zone. So if you look on the transform, we're already there. There's this thing called boundary, and you select the surface. You say okay, and let me see. I believe that in the book I used here you have a choice. I use keep all sub elements. Okay, there we are. Okay. So notice that there is a boundary of that thing, and if you hide this, you see that the boundary is still there. So let me get it back. All right, good. Save it. Now we're going to apply the material properties. The material properties, there are different ways of proceeding from this point on. What I've suggested in the book, that we go to the tools. You see on the material browser, you add a material. Let's give it a name, chapter 5. The only reason I'm giving these meaningful names is that it's easier to locate them later on if you do a search. Buckling panel. Buckling panel. And we want to make sure that these two are checked. In the older versions of 3DEXPERIENCE, you have to go and check these, but it looks like 2021, they have made these defaults. So we say okay. Now what happens is that it does create a material with that name for us in the database. Okay. Composite panel, chapter 5, composite panel, right? So buckling, this is the one that I wanted to do. Right click. Now, there's two things you can do here. You can either define the composite properties here, or you can apply and then define it. I'm going to be consistent with the way it was done in the book. So let me go ahead and define my numbers here. Like click on the composite. This is going to be 0.0 point thickness, cube thickness 0.056, or maybe I'm not sure, 2 zeros 56. Okay, 2 zeros 56. But when I say okay, this will change into 0.006. That's because of the displaying of the numbers in my default. So we say okay. The other thing is that we define our simulation properties. You click on it, structure, Abacus Multiphysics, Mechanical, Elasticity. You click on Elastic and choose Lamina and put all those numbers that I had for you in the table. Okay, so let me see those numbers where this guy, E1, was 19.6 e to the 6, 19.6 e to the 6 psi. This other one was 1.89 e to the 6, 1.89 e to the 6. Poisson ratio is 0.38. Remember there was a typo in the slide that I showed you. G12 is 930,000 psi. 3. Okay. Yep. This one is 930, also 930,000. And this other guy, I'm using 630,000. All right. Okay. We don't need anything else. We're not specifying the strength property. We're doing a buckling problem, so nothing else is needed. And we say OK. Now we're going to right click on this. We say apply and select the part. Accept the check mark here. See the check mark? And this, we can close this. Okay. Now notice that the material properties has been applied, and in fact the numbers were inputted before. We could have applied it and then change it right here, but this is not the approach that I took in the book. Save everything. All right. Okay, so now we are done with the first part. So we're going to go to the composite design workbench right there. Wait until this thing opens up. Now notice that it did not go into the same part. It started a new part for me. So let me close this for a second. And I'll tell you why this happened. Because actually it did apply it, but I'm in assembly design. If you go to part, notice that it did go to the composite design workbench, except that, you know, the way I showed it to you is that it took me to a new part, but it was there, okay? Uh, when I double click on the part, you can see that you're in the composite design work. Okay, so we're going to use the zone design. The first thing that we're going to do is specify the composite properties. Now, add material to the library. Now notice that I cannot pick this. I have to go to the database, material database, etc. And there's another way of doing this. Let me cancel that for a second. And this is how I'm proposing in many of the chapters in the book. What you can do is you can go to material definition. Go to the robot up there. Select material definition. What happens is that it takes immediately anything that's in your session, any materials that in your session, which was this is the only thing that's in my session, and makes it accessible to you in this window. Okay, so let's go ahead and do the rest of the work. Composite design parameter, add material, library. Now I can go, and from that tab that has the material in sessions, I can go select it. Okay, for my case, it was this top one. This is the one. Notice that they did put it in there. All right, and then let's go ahead and select our rosette. Now the rosette I did not specify, but uh, uh, let me be consistent with exactly the way it's done in the book. So I think I did the rosette. Yes. Yeah. Okay. So that's fine. Uh, I did not create an access system here, but that's okay. You say add a rosette. Now, if you put the cursor here, if I had already created a coordinate system, I would go pick it. But if I didn't, you put the cursor on this axis system, right click, insert wireframe, create axis system, it will automatically do it for you. And by default, of course, it puts in that position, which is the actual location really doesn't matter to me, but the directions are, and directions are correct. Z along the axis of the cylinder, as you can see. And let me uncheck the current and say OK, and then OK. So I did create a rosette. In fact, if you zoom in closely, you can see the rosette is there with the default angles. All I need is 45, 90, and 0, but you can see it. It's right there. Okay. All right. Good. Now, the next thing I want to do is to create a laminate. So I go to laminate, add a laminate. Now I'm going to use the stacking sequence. Material is the one that that's in the session. Remember chapter 5 buckling. And I start adding my orientation. So we say 45. The first one is 45. Add. Okay. The next one is minus 45. Add. The next one is 90. Add. Then there are two layers of 0. Add. One more. Add. And then there's a 90. I'm following this. See that? 90 minus 45 and 45. So where am I here? Yeah, 90, add, and 45, add. Okay, now I want to repeat this thing because the symmetric sequence. But the alternative is to use the symmetry option down here. Excuse me. Oh, non-pivot, which means repeated. See, 45 minus exactly the mirror image of that, and that's it. We say okay. So it created my laminate. See that? 16 layers. Okay, and that takes care of this, at least this dialog box. Okay, save it. All right. The next thing I want to do is to create my zone. I'm going to approach, you do this thing with zone method. So zone group. All right, zone group, the surface is right here. Keep the direction the same, the outward direction. Notice that the draping direction is outward. Keep it like that. And we say okay. So zone has been created. You see that right here. Zone group 1. Zone group 1 has been created, but no zone yet. So we do the zone now. Here is the zone. Select it. Now for the zone, remember it needs the boundary of the zone. Remember you extracted that boundary. You can do it either from the screen or from the tree. There we are. This is the boundary of the zone. For the laminate, I created laminate 1. So that's 16 layers. And everything else is fine. Okay, so let's save. And you now this is the zone is created. Now we're going to create the 16 plies from the zone and the laminate. So it's right here. See that? Plies from zone, right there. Plies from zone. Zone group 1, there's only a zone group. Make sure you check this box because otherwise you get a warning message, but it will create the plies for you. But if you don't like warning messages, check this box and we say okay. As I said, this is not the only way of doing the problem, but this is the approach that I've taken. There's going to be 16 plies here. Now we want to make sure that actually it's exactly the way we want. Now remember, to do that, you have to use the ply exploder to draw the plies. So to the ply exploder, you can access it by going to the plies design, review, and there's a ply exploder, group 1, and apply. There. It created the 16 plies for me with the angles that I want, but the order is not correct. Okay, the order is not correct. So I have to fix this thing. Now, one thing you can do is, first of all, I can cancel that. You can go one by one and fix the orders, fix the angles. But there is an alternative way, and that is to create a ply table and then go to the ply table in the form of Excel spreadsheet and fix the orientation and then import it back. So that's the route that I'm going to take. And so where is that thing? You go back to Plies Design, right there, Plies Design. Go to the ply table. Okay, it says, well, where do you want to put this thing and what do you want to call it? So to decide on where we're going to put it, you select these three dots. Okay, this is somewhere on my, I think this is on my local drive, yes. Video chapter 5, ply table. I'll call this thing buckling. Buckling panel. And the only reason I give these names is that it's easy to spot them later on. Buckling. Okay, very good. And we say okay. And open the stack-up file as soon as you create it. Otherwise, you have to go and get that Excel spreadsheet and open it up. So you have to select this plies group right there, because there may be multiple plies group. The question is which one you want to write it for. There's only a single ply group, and you say okay. So the Excel spreadsheet opens up, and you'll notice that in column E, those orientations are not correct. So let's start fixing it. The first one was 45. The next one was minus 45. Then it was a 90, and then 0, and then 0, and then 90, and then minus 45, and then 45. Okay, and this has to be repeated, but I'm going to copy and paste it here. Right click, copy, and then from here on, paste it. Okay, so this is the one that we want. Make sure you save it under the present name or a modified, whatever you want to do. I'll just save it under the present name. So we close this, and now we go apply table import. So it says, where is the thing that you want to import? Remember, I know exactly where it is. Three dots. Scroll down. This is the one that I just modified and saved, and we say OK and OK. So now when we use the ply exploder, it better be the order that we want. And I think it will be review, ply exploder, ply group 1, apply. And notice that it is correct now. 45 minus 45, 90, 0, 0, and then minus 40, 90, minus 45, 45, and then repeat it. This last one is actually your reference surface. Okay, this last one, there's 17 things here. The last one is just that panel that you drew, okay? And we say okay and cancel whatever you want. Cancel. All right, so let's save everything. So the plies have been created. From this point on, it's really the finite element stage. So you go to structure model creation. We are doing a structure problem. Notice that in the tree, you have nodes and elements and properties, branches are created, but there's nothing in it because you have to do the meshing and properties. So first of all, to do the meshing, that's the order that I'm doing in the book. You go to mesh, use a surface quad mesh. You select that surface and the size 0.5 inch. This is good, quadratic or parabolic. And then you say mesh to see it right away on your screen, right there. This is the mesh that you got. And we say, okay. All right. Now, the other thing is that if you want to specify the properties, so you change this thing to model, from mesh you go to model, and what you want is on the shell section, you go and get the composite shell section. Notice that not these two. This is a continuum shell section, which is something that we're going to be doing later on. This is, again, something else. And this one is composite shell section. Now the support is that split is you can either select it from the screen. In other words, that split that you did, right, was split right there. You can select it from here, or you can put the cursor there and select it. Doesn't matter. Okay, split. And by as far as the composite is concerned, we're going to do it by plies. It says, okay, where are your plies? Well, it's in plies group 1. And under advanced, this is very important. Make sure you use, with this pull down offset, select none. What this means is that this stack that you're going to create, these 16 plies, uh, half of them are going to be above this cylindrical panel, and half of them are below. So that's what this no offset means, zero offset. Okay, and we say all right. Okay, save everything. Notice that the elements have been created, the properties have been created, and we are done in this. In there, we're going to go to scenario, structure model creation, scenario creation. It is a structural problem that we're doing. And you get the two red exclamation marks here, the usual stuff. Let me hide this. Okay, so you go to the setup, select your finite element model. There's only a single finite element model here. You select it. As soon as you select this and say okay, this red exclamation mark turns into green. You see that? And then the procedure, you're going to do buckling. There it is. This is static. Okay. Later on we're going to do dynamic. Okay. But right now we're going to do buckling. Now, keep all the defaults, but I can guarantee you that we may have to come back here, that this is not sufficient number of iteration, maybe because of the mesh size. And the software will bomb out, and we're going to come back and fix this, okay? We're going to come back there. Okay, so now we're going to apply our a load, for example. Okay, be careful. Now, you see, my suggestion is that if you want to, let me, okay, let me select this. I selected that edge, okay, and I'm going to say shell edge. You got to be very careful, because it could be that this thing that you pick comes from actually it's the actual boundary of a ply, etc. So what I suggest, before you do that, hide some stuff. For example, go ahead in the part. There is a part. Hide the sketch that's already hidden. Hide the extrude. Don't hide the extrude. Hide this. Hide the boundary. Hide the boundary. Okay. Hide the stacking. Hide the stacking, engineering stacking. Because I don't want to pick the edge, which is actually the edge of a zone, etc. Hide the zones, and you put the cursor. Where is that? You put the cursor there. The cursor there. Right click, hide. Okay. See that? I think this is the edge of the panel now. Okay, so first of all, let me save everything. If I don't want to see my mesh, it's very easy. There are different ways of doing it, but one way is you put the cursor there and you say mesh visualization or visualization management, and for the finite element model, say don't show me the model. Okay, I can just see the part. Okay. Now, so we're going to go to loads, shell edge load. See that shell edge load, and you select this edge. Okay, and it's compressive. Compressive by definition is a positive number. So we put a 1 pound per inch here. This is 1 pound per inch, and we say okay. All right. Remember, this is this. If you look at that drawing, we're compressing it in this direction. Okay, fine. Now the other edges are all simply supported. So we go to what is that? Restraint. Okay. This top one, all three translations are fixed, so we go fix displacement on this top one. All three translations are fixed. And the other three edges, just the X and Y translations are fixed. One, this one, and that one. And that one, 3 edges, no displacement in X, no displacement in Y. Of course, these should be able to displace in the Z direction because we're compressing these edges, right? We say okay. All right, save everything. Okay, so we're going to go to simulate. Let's do first of all model and scenario check. Hopefully we're not going to get any error messages. Warning we can live with. Okay, so close. Then do simulation check. People get complacent and they don't do these things, and sometimes they run a problem that takes a long time. Eventually, it doesn't work because they didn't actually check these intermediate stuff. Okay, it's not running yet. It's not. It's just checking the scenario basically simulation. You get a warning here. It's a good idea to read these things at some point, but my bad habit, is that I don't read it until the system crashes or the software crashes. Then I go and see what is it that it was saying. Okay, this one successfully finished. And finally, we're going to run it. And this is where we're going to have a problem. As you will see, it will not run. It will give us an error message, and we have to go fix it. Okay. Yeah. The one thing you notice is that we didn't specify anything, the nonlinear geometric effects. So because those are when you do linear buckling analysis, that's already built in. Okay. So in the previous chapters, I always went and unchecked the nonlinear or nonlinear geometric effect. But here I didn't have to do that. Didn't even give me the option either. So here's error one. Okay. And if you read it, you see that, well, I'll show you. They'll tell you that you have to increase the number of iterations. Okay, right there. Increase the number of iterations to get the requested number of eigenvalues. So we close. How do we do that? We go to our buckling step. We go down here to the buckling step. There it is, right there. Double click on it. Remember I said I was going to come back? Make this thing 100 instead of 30. And since I didn't change anything else, I'm just going to simulate. I'm going to run it. This time it will run, and it will give me a table, as you will see, with buckling load at different for different modes. Actually, these are not buckling loads; these are called eigenvalues, and I'm going to show you how to get the buckling load from those eigenvalues. It's very simple. Just taking that and multiplying it by something. I'll show you what the something is. Okay, it's going. This is the only thing that we want to see. We want to see the buckling load and the buckled shape. There's nothing else you can do with this analysis because this is linear and it will give you just a very simple initial design configuration. Okay, it did run, extracting the result as you can see up here. Okay, there we are. Okay, right there. So first of all, I don't need this. This is what happened. This is the first buckling shape. Look, when you compress this thing, the other edge is simply supported. At some load, it look like this. Then you go to the next one. The other one is a different buckling load. You can see that. And then you can go and get all of these. Okay. Now this is the shape, although the actual displacement is totally irrelevant. It's not important. This is why it's actually normalized, but it shows you anyway. It shows you anyway if you ask for it. The question is, okay, what is my buckling load? Well, That's the first one, the critical one. It says eigenvalue. It doesn't say the load. So what you need to do, what this means is that take the load that you applied. Remember, you applied N, or the edge load. You applied edge load of 1 pound per inch. Do you remember that? You take that and you multiply it by this number. So my N, which incidentally, it was a bad idea to call it, if you look at this diagram, we call it NX. This is a bad idea. I should have called it, this is a bad idea. It should have been NZ, not NX. Ignore this, please. It's NZ. The NZ, I specified it to be 1, and that gave me this number. So if your NZ is 1 times 1,671, okay? That is the critical edge load, 1,671 pound per inch, okay? The question is, what is the force? Well, the force, you need to go and you take the perimeter, see this perimeter, this perimeter, this perimeter, which incidentally is uh, 14.55 inches, okay? 14.55 inches, multiply it by this 1,671, and I don't have my calculator here, but it's going to be something very close to this. So actually, I can tell you what it's going to be. If you do that calculation, you will get uh, 24,313. So this is from that reference from back in 85, and what we get with 3DEXPERIENCE is 24,313. Now remember, my mesh was very coarse, and I didn't look into the effect of the mesh here, but basically that's what it happens. So about a bad notation here, this should be NZ, and then take your eigenvalue, multiply it by the NZ that you applied. This is why I applied only 1 pound per inch, so that I can directly multiply it by my 1,671. Okay, I applied NZ equal to 1. The critical eigenvalue came out to be 1,671. So I take the 1 that I applied, multiply it by 1,671, and then multiply it by the length of that arc, and that'll give me a force. Okay, folks? Good luck.